I have graded the homework 1, and I don't know, are you able to see it? Okay, under the homework submission folder. The problem is that it's not PDF, so I cannot grade it. It's Excel file, but I try to capture the comment. What are the things that I think you didn't do correctly? So for example, let's say your lambda extraction is wrong, or your mu and COX extraction is wrong. I notice a very common thing is that you guys, a lot of you, didn't put significant number of digit, especially for the lambda one. So a lot of them is like 2 times 10 to the power minus 6. But it could be 2.1, it could be 2.22. So without showing the significant digit, your gradient extraction could be greatly affected. Okay? And in Excel, there is actually a way to change it. You guys can Google and figure out. So these are the common mistakes that I find. I think most of you get a pretty high mark. Except that I think a few of you actually didn't plot according to what I required. Instead of plotting square root ID versus VGS, some of you still plot ID versus VGS. And then you're trying to extract the gradient. Of course, it's wrong. Okay? Today is going to submit homework 2, right? No? Or next week? By the way, the project, the deadline is actually on 11 April. Any issue? Suddenly quiet. No issue? Very happy? That's why I'm asking this question. Because unfortunately, 11 April is week 13. Extend another week, we are going into the reading week. Another week, exam already. Okay? So probably I can extend it all the way till the Friday of that week 13, which means 11, 12, 13, 14, 15 April. Or you want the next Monday, so you can work on over the weekend. Next Monday, okay, fine. I'll change I don't want to change the project, but anyway, you guys know. I will make an announcement. The project submission deadline will be on 11 plus 7, so that should be 18 April. Okay, 18 April. Okay. Last Monday is a very long lecture. I hope I don't have to do that for today's lecture. Last Monday we covered a lot of things. We covered some example about RF amplifier. Okay, I introduced a concept called fictitious resistor. It implements a real impedance, real part of the impedance, without actually behave like a physical resistance. Okay. And then we talk about the differential pair. I think for differential pair, the important concept for you to know is the so-called common mode rejection. Common mode rejection. And then what is the difference between differential circuit versus different circuit? And you will notice that the CMR is a big difference, right? About 40 dB difference. And then we start looking at current source, and the upcoming homework 2 is about current source design. Okay? So there are 4 different methods that we talk about current source design. Basically, scope current source design. We want the output resistance to be very, very high, and yet the headroom is maximized. Okay? So there are 4 different methods. It depends on your preference. You can use any 4 of them, but do be aware what are the limitations for these all 4 components, for all these 4 methods. And then finally, we quickly introduce the so-called active load. Then with the active load, the beauty or the advantage is that it gives you a very high output resistance without actually sacrificing any voltage headroom, right? And then we conclude the whole lecture with one example, which is the common single-ended output 2-stage or operational amplifier. So we covered that, and then we show you the design example. So today, we are going to shift a little bit. We are going to talk about another very important building block in circuit, which is called bias. So you know that a lot of time in the circuit, for example, ADC, we need reference voltage. So we want to generate very unchanged, very constant voltage reference, so that it doesn't matter where we use the ADC, it always works, right? Or we want to generate something that is totally independent of temperature. So when you create a voltage that is 1 volt, for example, it doesn't matter whether it's operating at 0 degrees Celsius or operating at 100 degrees Celsius. It's always 1 volt, so it's temperature independent. Or we want to create something that is totally supply independent. For example, it doesn't matter whether you power the circuit with 5 volt or 3 volt. I always get reference voltage of 1 volt. Okay, so that is the focus of today's lecture. And then we will quickly move on to looking at the frequency component. Okay, we'll introduce something called gain bandwidth product. And then we'll look at how people look at or identify or analyze the frequency response of the op-amp. And finally, we'll bring in a very important topic called stability. So if you talk about op-amp, if you use op-amp in a negative feedback circuit, you always have to deal with stability, and that is the big issue. Okay? This is very interesting. If you talk to analog designer, they always tells you stability is the big concern. Okay, the circuit might be unstable. You talk to RF, they also told you stability is the big concern. So in your thinking, stability is something that if you don't pay attention, you can easily get it, right? Which is true. Which is true. Can you name one unstable circuit that is very useful? Oscillator, right? Oscillator is something that is unstable. We want to exploit it. But does it mean that oscillator is easy to design? Easy to design? No. So it's very easy to create instability. But it's not easy to create instability in a stable manner. Okay? So that is the thing. A lot of students think that, oh, create oscillation is very easy. True. But we want to create good oscillation. That is another story. Okay? So here we are mainly talking about stability in the sense that we don't want it, especially in negative feedback. So let's look at supply independent. When I try to introduce the topic, I try to emphasize on something that you right away can take away. Okay? Supply independent. If you think about that, how comes people come up with this kind of circuit? It's actually, the idea is very simple. If you can identify some parameter that is very well defined, then whatever the things that you created would be sort of independent of the supply voltage. For example, what is the diode turn-on voltage? If you don't know, you shouldn't be in this class. What is the well-known turn-on voltage of silicon diode, for example? 0.7, very well known, right? So if you think turn-on voltage 0.7, if I can somehow exploit this parameter in my circuit, then this voltage will be totally independent of other things, am I right? Because it's sort of universal, it doesn't matter, okay? It doesn't matter whether I'm using 5 volt supply, 3 volt supply, it doesn't matter whether I'm using 100 degrees Celsius, 0 degrees Celsius, 0.7 volt seems to be quite well known and constant. So this is the parameter that we exploit, okay? So once you know of this principle, then supply independent biasing is not too difficult concept to grasp, right? You will know. Let's look for some parameter that is unique of some device characteristic and then exploit it and then create a circuit out of it. Then we will be able to create some supply independent biasing. So let's look at the first one. So the first one, we just simply exploit the well-known characteristic for BJT. So for BJT, when we say the BJT turns on, what is the VBE? What is the VBE? 0.7, same as diode, right? So therefore you can see you are applying the VBE across the resistor R. So 0.7 is almost there. It's more or less there. It doesn't change. You apply this 0.7 to the resistor, whatever the current that you are getting will be independent of the supply. Am I right? Assuming the resistor doesn't change, which usually you can do that. Okay? So some of you might be saying, okay, but resistor did change with temperature coefficient. But you know, we can do this kind of thing. R1, R2. R1 have positive temperature coefficient, R2 have negative temperature coefficient. They cancel out. So what does positive temperature coefficient means? The resistor increase with increasing temperature. Negative coefficient means resistor decrease with increasing temperature. So you combine the two. One is increasing, one is decreasing, they cancel out, constant. So you can actually do this kind of resistor to make sure that in the end the supply is still independent. The biasing that you are creating, the I naught, is going to be independent of the supply. Okay? And of course for MOSFET, they don't have the well-defined VBE, but they do have VGS. So here, if I can somehow make sure the current going through is a well-known number, let's say 1 milliampere, it doesn't matter what the supply is, I always pump 1 milliampere, then you can actually establish the VGS. Okay, you can see that the VGS is actually only depending on the reference current that you pump in. So let's say if you are able to create a current that is more or less constant, and then you pump into the VGS, you establish a constant VGS, and then you apply this guy across the resistor, you're able to create a current that is again independent of the supply. It doesn't matter whether you are using 1 volt, 2 volt, 3 volt. Okay? And of course, this is less popular in the silicon because in CMOS IC it's very difficult to get Zener diode. In CMOS IC, we are talking about supply voltage that is probably below 1.8 volt. Nowadays it's 1 volt. Zener diode, usually the breakdown is in the range of 5 volt, 3 volt, or even 7 volt. Right? That is very high. But nevertheless, in the past, we do use Zener diode. The thing is that when Zener diode break down, the voltage is well defined. So this Zener diode, it depends on the doping. So when you create the Zener diode, you create using different doping. So some Zener diode, when you break down at 5 volt. Some break down at 7 volt. Some break down at 9 volt. But once you break down, you always break down at that voltage. So if you make sure that this Zener diode is break down at exactly what you want, the voltage, and then you can see that this voltage will be applied across the resistor R. Okay, it should be quite clear to see this is VBE, but the other guy also VBE. They sort of cancel out each other. So it means the Zener voltage is directly applied to the resistor, and therefore the current is again simply a function of the Zener breakdown voltage. So this is the very simple principle to create a supply independent biasing. You identify some parameter that is independent of the supply, and then you can create a current in that manner. Okay, so let's apply that principle. Just now we only show the bottom half of the circuit. Okay, you can see this guy. We create this bottom half of the circuit. But let's apply what we have learned about the active load or the current mirror. Okay, we have this branch already at the bottom. We know that the current created will be totally independent of the supply. But why don't we just add on top a current mirror and then make, because of the current mirror, these two branches of the current will be equal to each other. Right? That is the beauty of current mirror. This current mirror makes sure that IQ3 equals to IQ4. Right? That is the purpose of this current mirror. That is the purpose of this current mirror. So let's look at what happened. At the bottom, we already know. At the bottom, we have this output current equals to VBE over R. The VBE can be further expanded using the following formula. Okay, the following formula, which is basically IC1 VT ln IC1 over IS1. Okay, but IC1 equals to VBE1 divided by R. Okay, so you can write down this formula. Now, this formula basically just tells you this solid line over here. So this solid line basically describes the function characteristic with the ln function. Okay, in fact, I naught is IC2, and then this guy is IC1, so therefore you can actually come up with the relationship IC2 and IC1 related in the natural log algorithm, so which is described by this solid line over here. Okay, so this solid line actually describes the IC2, IC1 relationship. Now, the top basically create a current mirror forcing IC2 equals to IC1. Right? So what is IC2 equals to IC1? Which is this dashed line over here. IC2 equals to IC1. So the bottom circuit create this log function. The top circuit create this dashed line function. What is the solution? At equilibrium, the two currents should match, right? That is KCL. Okay? So it means these two functions, these two curves intersect. That will be the solution. So therefore, this intercept point and this intercept point would be your solution. And both are acceptable. Both are the correct solution. In that case, which one will you choose? We don't like ambiguity. Okay? If there are two solutions, we don't like ambiguity. You can pick either one, but once you pick, better always be that point. Okay? So, to solve this problem, one way of solving it is you disturb the equivalent. How do you disturb the equivalence? You introduce this IX to the IC1. So you add IC1 with IX over here. Okay? So in that sense, you are actually making IC2 actually wrong. So this side is actually you are making IC1 equals to IC2 plus IX. Right? That should be, let me redraw. This is IC1. This is IC2. So here is IC2. So IC1 is basically equals to IC2 plus IX. You can see that clearly, right? Yes or no? So, if that is the case, let me see. So in that case, your IC2 will be equals to your IC1 minus away IX. So here, okay, this is equals to IC1. So now what you want is IC2 equals to IC1 minus IX based on this guy. So therefore the dashed line would shift it down by the amount IX. Why do you want to shift down? Why do you want it to shift down? You want it to shift down so that now the intercept, you will notice one of them is shifted to here, another is shifted to here. Now, the left-hand side, the intercept point, when you shift it down to here, what you have is actually a negative current. And you know that in the circuit, this solution doesn't make sense. Negative current means the current flowing outward, right? But if you look at the circuit, the current should always flowing downward. So therefore, you right away know that although there are still two intercept points, there are still two possible solutions, but you know that now there is only one solution that is physically meaningful. This guy over here. So by adding one additional current, you are actually forcing the solution from two solutions to only one. Okay? So in that case, you guarantee that there is no ambiguity in your solution. Now, then if you look at this guy, this solution, when you solve everything, does the VDD come into play? You look at all the formula. Did VDD appear anywhere? No. So therefore, we call it supply independent biasing. So the concept is very simple. You make use of some parameter that is well known, VBE, for example, and then you establish the equation, and then you try to force the left-hand side and the right-hand side to be equal using current mirror. And then that's it. You solve the whole thing. And of course, it will give you two solutions, but you can actually eliminate one of the possible solutions by disturbing the equation. Okay, so that is the whole principle. Now, how do you disturb? Now, disturb is not good. Disturb in the sense that when you disturb it, you are introducing IX. So your solution will be depending on what you introduce. Am I right? But when I introduce, there is no guarantee that whatever I introduce is well controlled. So you can see that from that solution, if I introducing slightly more, I will intercept here. I introducing more, I will intercept here. Right? So in the end, the solution depends on what I introduce. So that I don't want. I want it in such a way that eventually it will settle down to without disturbance. Okay? So why do we introduce disturbance? It's like you introduce disturbance, it's like buying insurance. You insure yourself that by introducing the disturbance, I always get to this right-hand side solution. But once I guarantee I get to this already, you remove the disturbance so that it doesn't affect your final solution. You get the point? So that is the whole principle. Now, if you understand this, then this slide becomes easily understandable. Okay? So, what you have over here is still pretty smart what we talk about, supply independent biasing. Now, this branch IX is what we try to introduce. So, at the startup, we try to introduce this IX. Why? Because I know there are two solutions. So, during startup, I want to make sure this solution doesn't make sense. So, I introduce the IX. But once I start to get that solution already, I want to remove the IX. Okay? So, the whole principle is that if you look at this circuit, it should be quite easily understandable. Initially, you introduce IX as long as VB bigger than VA. The diode will flow the current and therefore introduce IX and therefore disturb the equation, and you will end up having the right-hand side solution. But once the whole thing starts to establish, if you are able to design such that VA bigger than VB, then the diode is reverse bias. And therefore you cut off the IX. The IX is no longer there. And therefore you go back to the original desired solution. Get the point? Okay? So to answer this question, basically you establish the equation. Your VA is simply given by VBE1 and then VBE2. Okay? And then you have this IC2 plus IX multiplied by this resistor RX over here. Okay? And you can replace the IC2 using this VBE1 over R into the equation. So you end up having something like this over here. Okay? So your VA is this. Initially, your VA is this. Now, your VB is very well understand. You have 4 diodes. So your VB equals to 4 VBE. Okay? So your goal is to make sure that during startup, your VA is less than VB. During startup. That should be quite easy to establish because at that moment you can select, let me see. So your IX, it cannot be too big, but you can select R over Rx to manipulate the voltage so that this guy is actually less than your VB. Okay? But once you start establishing the voltage for the VBE1, VBE2, you want to make sure that this guy is now bigger than your VB so that it will be cut off. So you need to pick the Rx carefully so that at equilibrium, this whole equation, VA, is actually now becomes bigger than your VB. So in that case, you can turn off the Ix and then you end up having this solution over here. Okay? So for supply independent biasing, one of the issues is that you always need startup circuit. Without startup circuit, you end up having ambiguity in your solution. Now, this is the MOSFET equivalent. So for this MOSFET equivalent, the idea is the same. We establish the VGS across the R so that the supply is only depending on VGS. It doesn't depend on the VDD. And then on top, we use a current mirror to force that this current, let's say IM3, is the same as your IM2. So we use this to force the current to be equal. Okay? So the idea is your ID2R is exactly equals to your VGS1. And your VGS1 can be established using this formula. So for those of you who doesn't know how this formula comes about, ID1 equals to half mu n COX W over L M1, and then we have VGS1 minus VTH1. So square. So if you move this thing over and you take the square root, you end up having what is your VGS1. Okay? So if you try to plot this guy, you will see that it suffers exactly the same thing as the BJT equivalent. You have two equivalent circuits. So for this guy, you want to make sure that initially you disturb the circuit. So how do you disturb it? You introduce additional current to this branch. Okay, so ID2 plus IX will be equals to your ID3. Sorry, ID3. Okay, so your ID2 now is equals to ID3 minus IX. So same thing, you are trying to move it to a negative point. But once you establish the circuit, so everything's set out properly already, you want to turn off M10. You want to make sure that M10 is turned off. So if you look at this circuit, you'll see that initially, when you first turn on, the VA could be stuck at VDD. Okay, VA could be stuck at VDD. So if VA is stuck at VDD, there is no current flow, or very small current flowing. So that could be one of the possible solutions, which is not what you want. But when that is the case, initially, you think that this PMOS always on because it's connected to ground. Okay. And because this is very high, this is VDD, so M6 is cut off, so doesn't turn on. So if it doesn't turn on, then there is no voltage established over here. Your M9 is also turned off. So initially that is the case. And because M7 is on, so VB now actually is high, VDD. Right? So if VB is high VDD, M10 turn on. Once M10 turn on, you will start to draw the current. And because it starts drawing the current, M4 would now have some current flowing through, and your VA will start to drop. Your VA will start to drop. So that is the initial starting point. Now then, when the VA start to drop, what will happen? Now if VA start to drop, you will start to have current flowing through M6, because current mirror, right? And if this current flow through M8, you will start to establish the VGS. So once you establish this VGS, M9 start to turn on. Now if you pick M9 much stronger than M7, okay, you can consider this like, this is a register, this is another register. Now if M9 is much larger, this register R9 is going to be much smaller than R7. Agree? Right? So at equilibrium, when R9 is much smaller than R7, your VB is going to drop close, or you just need to make sure that it is dropped below the VTH of M10. If it drops below the threshold voltage of M10, M10 will turn on. Right? So that is the whole idea. So initially, when it first start up, VS stuck at VDD, M7 turn on, M6, M8, M9 all turn on. So M10 will turn on to draw the current. Once that is happening, M6 start to turn on, M8 start to turn on. That will cause M9 to turn on. You just have to select the sizing of the M9 such that when M9 turn on, it presents very small resistance so that the VB drop below the threshold voltage of M10. Intuitively, that is how you design the circuit. Okay, another important circuit, PTAT. The full name is proportional to absolute temperature. Proportional to absolute temperature. Now the key idea is actually very simple. You are trying to create a voltage difference across the register. But that voltage difference is actually the base emitter voltage difference across two transistors. So from this circuit, it's quite obvious. You have VBE1 on one side. You have VBE2 on the other side. So the voltage across here is actually VBE1 subtract away VBE2. That's the idea. We are using two transistors to create a VBE difference across the register R. That is the whole idea. Why that leads us to PTAT? Now, if you know, your VBE1 can actually be established using this formula. For those of you who doesn't know why, IC1 equals to IS1 exponential VBE1 over VT. So therefore, if you take ln on both sides, you move this guy over, you have IC1 over IS1, take ln, multiply by VT, and then that is your VBE1. So So it's actually coming from the BJT exponential relationship. So this is your VBE1, this is your VBE2. Okay? Now there is a subtle difference between these two BJT. These two transistors, you purposely pick one of them to be A times larger than the others. You pick Q2 to be A times larger. You can consider this as this. A times larger, you can consider it like I am having A transistor, A number of transistor, bigger than Q1. So let's say if Q1 is 1, if I pick A to be 10, it means Q2, I have 10 Q1 in parallel. Equivalent like that. So by doing that, what is the advantage? What is the advantage? Now you can see that because now you actually have A times transistor, your IS2 is now also A times IS1. A times IS1. And then your top, you are using the current mirror to force IC1 equals to IC2. So current mirror is very, very useful. You use that, you always try to force the two branch current to be equal. In log function, subtracting actually means division. So you can actually combine the log. You have IC1 over IS1, and then you divide by IC2 over A times IS1. Okay, so it's actually ln IC1 over IS1 multiplied by A times IS1 divided by IC2. Now you start to see, because IC1 equals to IC2, they are equal, so this cancel. IS1 equal, so they cancel. So you end up having a very simple expression. Your output current is simply equals to VT divided by R multiplied by ln A. Ln A is a constant. It just depends on the number of transistor ratio between Q1 and Q2. So if Q2 is 10 times larger, you can consider it as having 10 Q1. Okay, 10 is a nice number that we always choose. But very importantly, you notice this current, what is VT? VT is KT over Q, isn't it? Right? That is VT. We call it thermal voltage. And the name is quite telling. KT over Q, thermal voltage. K is Boltzmann constant, so it doesn't change. Q is the electron charge, also constant, doesn't change. But thermal voltage, it means this voltage is directly proportional to absolute temperature, Kelvin. Right? At 27 degrees Celsius, you are getting 25 or 26 millivolt. At 0 Kelvin, of course, you get 0 volt. Okay? So this thermal voltage is directly proportional to the temperature. So in fact, you can use this to create a simple analog temperature or thermometer. You just need to measure the voltage over here. Okay? The voltage over here is simply given by VT ln A, so that gives you KT over Q ln A. So you can see it's directly proportional to T. So you simply measure the voltage across the resistor R, you are going to get a temperature reading, provided your R is temperature independent. If the R also depending on temperature, then whatever that you measured also get messed up by the resistor. But I already show you a way to remove the temperature dependency of the resistor. Am I right? You use two. One got positive, one got negative, they cancel out. Then in that case, you are getting temperature independent. So this is how we can create PTAT source. Using this manner, always use the difference of the VBE voltage between two transistors. You are able to create a proportional to absolute temperature biasing over here. So you can see that if you want to create a totally temperature independent biasing, another way is you mirror this current. Okay, so this current beside the VT, you also have something that is proportional to the temperature R. Okay, Then you multiply this current with another register R1, but you make sure this register exhibit exactly the same temperature coefficient as R, right? So if you R1 and R are of the same type of register, then when this guy increase, this guy also increase, they increase the same way. You divide them, you get back the constant. So that is how you create temperature. You create a voltage that is proportional to the absolute temperature. Where is R1? You can pump this guy into a register, call this guy R1, but you pick R1 and R at the same type. The same type. Same type. You know register, there are many different types, right? There are thin film register. They are using tungsten wire to make the register. All these different material actually contribute to different temperature coefficient. So this method, it doesn't matter which register you're using. You just use the same type. Then the temperature coefficient will cancel out each other. That's nice. That's nice. So here, if let's say we are not getting the output voltage, we are getting the current, and somehow you didn't pick R that is temperature independent, then if you try to figure out how would the current changes respect to temperature, now this is a very important way of identifying how certain quantity changes with respect to temperature. So what we do is we always find a gradient. We find that quantity gradient with respect to temperature, and then we divide by that quantity. Okay? So you can see what we do, we find the gradient of the output current with respect to temperature. The gradient of output current with respect to temperature that show you how the current changes with temperature. But we don't want current, we want the absolute number. So we actually divide that current with the absolute current itself to get rid of the current dependency, to get rid of the current quantity itself. So that's why we divide by 1 over I naught over here. So if you try to determine the delta I naught over delta T, which is this guy, you will end up having the following. Okay? Notice that one of them is basically just taking the linear equation of the VT. Another is actually have to consider the register dependency. And then you divide by I naught. Okay? So you end up having the following. So 1 over T is about 3,300 parts per million. What does parts per million means? It basically means 0.003300. That is like 3,300 divided by 1 million. That is what it means. Okay, parts per million. So if you read the data sheet of a lot of components, you will see this guy. The component change by how many parts per million per degree Celsius. Okay, this is especially true, for example, for crystal oscillator. They will tell you, oh, this frequency changes, the temperature dependency, 20 parts per million per degree Celsius. Okay, they just basically normalize the quantity. By dividing the current with the current, you remove the current quantity. Therefore, it becomes parts per million. If you are interested in frequency, you divide the frequency with frequency, also parts per million. If you are interested in voltage, divide the voltage by voltage, also get parts per million. Okay? So that is the beauty. You no longer bother yourself with what quantity are you dealing with. Okay? Eventually, you know the parts per millions. If it is frequency, you just multiply by frequency, you know how frequency change. That is the beauty. Okay, that brings us to why do we introduce PTAT? Because with PTAT, what we do is we create something like this. If we try to plot temperature, I naught, or VB, or V voltage, let's say V reference, we are creating something like this. When the temperature is increasing, our current quantity or the voltage quantity also increase linearly with temperature. Now, band gap reference, the key idea is that, are we able to create something that is like this? That is a CTAT. is it, I don't know the name, maybe it's called complementary to absolute temperature. Okay? So you have proportional to absolute temperature. You have complementary to absolute temperature. All it means is that it's like when the temperature increases, instead of linearly increasing, now I have linearly decreasing. So this guy we already know how to generate PTAT. Now if we can somehow obtain this guy, which is called CTAT, you combine the two. Let's say you sum the two currents together. If you sum the two currents together, you are going to get horizontal line. Am I right? Or if you sum the two voltage in series together, one is increasing, one is decreasing, you sum them together, you also get temperature independent voltage. Right? So although the name is called band gap, the key idea is basically you have the PTAT, let's find something that is CTAT. And then you sum the two together, you get horizontal thing. That is the key idea. So how do you do that? In fact, you don't have to create a component that is called CTAT. In fact, one of the parameters, what we call base emitter voltage, already exhibit this kind of characteristic. If you look at the VBET, which look at the base emitter junction voltage of the transistor, with respect to temperature, it actually looks something like this. It just happened that if you substitute T equals to 300 degrees Celsius, 300 degrees Celsius, right? No, sorry. 300 Kelvin, right? Which is 27 degrees Celsius, right? If you substitute this value into it, you end up VBE approximately equals to 0.7 volt. Okay? So the 0.7 volt is actually happening at room temperature. So if you try to analyze the VBE temperature dependency, it actually exhibits this kind of expression. It starts with one nice number, 1.205. And then you will start decreasing with temperature, and you will hit 0.7 volt at room temperature. So 1.205 is actually the band gap of the silicon. Okay, the silicon. So that is one of the reasons why people call it band gap reference. So if you somehow able to cancel this CTAT component with your PTAT component, so this guy got negative K1, let's say you come out with positive K1, the two cancel. These are higher order, you don't really care. Higher order, you can assume this higher order effect negligible, because the K2, K3 could be very, very small. Okay? Much smaller than the first order effect. So if you ignore all of them, so to the first order, this guy cancel, you are going to get back this voltage, 1.205, and that is what we call band gap. Okay? That is also the reason why people call it band gap reference. And that is good. Band gap reference is tied to the material, silicon. So as long as you use the same silicon, it's always this number. It doesn't change. Okay? So how to create this? Very simple. We already know how to create PTAT, which is this guy. So the current generated over here, this is actually PTAT current. Now this PTAT current, you multiply by this resistor, you are going to get PTAT voltage. Right? But this base emitter junction is going to give you CTAT voltage. Agree? You sum these two voltage together and you look at this guy. Yeah, it is going to give you a constant voltage. That is the whole idea. So your V reference is simply your VBE3 plus this PTAT voltage reference. Now if we ignore, so for example, just now we showed the equation over here. Let's ignore all the higher order term. We only take this guy. So we are going to get this guy over here. Now you can see by properly chosen R1 and R, okay, what you have for this gradient is basically, I write it out, Vg0 minus K1T plus R1 over R, K over Q, ln A multiplied by T. Right? Now, if I pick K1 equals to R1 R, K over Q, ln A. The two cancel out. Right? This term, the second term and the third term will cancel out. Because one is negative, the other is positive. They just cancel out. So then you're only left with one constant, Vg0. So that is the whole principle about band gap design. I think the project is related to this one. Okay, so take the concept. The only difference is like there is one issue with this band gap reference. I'll talk about that later. Now, of course, you will not get simply Vg0. In fact, you will get Vg0 plus all the higher order term. Okay, so there will be some residual. In fact, you know, in the very early day, there are people doing PhD by further looking. How can I cancel the second order effect? So first order, all people know already, right? But how about second order? So if you are able to cancel away the second order, so you are going to get something like this. Sorry, I didn't draw very nicely. You'll get probably something like this. You know why I know this? Why the curve look like this? You guys should know function, right? Have you guys learned about how to plot the polynomial function? Linear curve look like this, right? Square look like this or look like this. Third order look like this, right? So if you cancel away the second order, you will know that the curve will look something like this. Okay? But with smaller variation, yes. Third order. Because after you cancel second order, you still have third order, right? Now, if you cancel the third order, you end up having fourth order. But the fourth order, the curvature will be even smaller. It will probably look something like this. Okay, so the higher order that you cancel, the flatter it is. So there are PhD students trying to do that. Okay, people already done first order. Can I figure out a way to cancel second order or third order to make it even more temperature independent? Okay. Now, in fact, we simplified the picture. So this is a very simple way of understanding, which is great, But in fact, if you look carefully, we don't actually get 1.205. If you look at all the paper published in the literature, that tells you if you design a band gap circuit, you actually get 1.26. You don't get 1.205. Okay? So there are something that is somehow related to the process. So to be more accurate, you will see that the reference voltage actually, beside the Vg0, they also have this additional factor, gamma minus alpha. And then if this is the nominal temperature that you want to design with, and then the temperature dependency actually looks something like this. So beside this linearly proportional to the temperature, they have this additional term, the nonlinear term. And if you, after cancel the temperature fully, you see that eventually the process parameter give you about 2.2. So at 300K, so you put T equals to, let me see, okay, T0, and then this is 300K. So this guy becomes 0, but you end up having, you put 300K over here, and then there's a 2.2 over here. You put in, you will get additional 55 millivolt for this term. And that is the reason why the voltage is 1.26 volt, not 1.205. Okay, so these are just minor correction to the theory, but this theory is easy to understand. If I right away show you this one, it will be very confusing. How come the temperature coefficient look like this, right? But if I right away tells you, if you look at the circuit, the BJT, it actually looks something like this. Then understand the circuit, you know, oh, that is very easy. I just cancel K1 with all these things. and you will get temperature independency. So I will treat this guy as minor correction. Okay? And this is actually simple to understand, conceptual. Conceptually, it's simple to understand. Now, unfortunately, we don't have BJT commonly available. Of course, if you are dealing with bi-CMOS process, there is BJT. If you are dealing with BJT process, there is BJT. Right? But if you are dealing with CMOS process, there is no BJT. CMOS process don't have BJT. Because to create BJT, you need a lot more process steps. That's why CMOS is cheap. It requires fewer processing steps compared to BJT. Okay? So, but we do have some unintended BJT available. So if you look at CMOS over here, okay, we have N-well. This is N-well. So we can create N-well easily. We have P substrate. So these are available in CMOS process. And then we can do body implant. Right? This is P plus implant. And then under N-well, we can implant N plus, we can also implant P plus. Right? If you look at all these process steps, it's available in CMOS. P plus, N-well. This is actually PMOS device, right? And then at the body, you create N plus. This is the body, right? So you can see this is available, and then this N-well is also available. The P sub and the P plus also available. So all these things allow you to create a BJT. Why you need this is a BJT? You look at this guy. You have P plus here. You have N at the middle. You have P at the bottom. You actually have P and P. But this BJT is never a good BJT. Nevertheless, it is a BJT. Do you know what constitutes a good BJT? A good BJT looks something like this. N plus plus, followed by, maybe I will do P and P. So P plus plus, followed by N plus, followed by P. And this distance need to be very small. That will constitute a good BJT with beta of 100 to 200, right? But what we have is something that we create out of what we have, right? So the N-well, first of all, is not going to be thin, and you cannot control the depth. Secondly, the doping is not good. It's not very high. The only thing good is about the emitter, P+. This is the only good thing about it. And then for collector, there is another thing that is missing. If you remember, we usually have buried region, P+, buried region. And then before we connected to P+ over here. The reason for this buried region is because in BJT, the current go to the bottom, and then you have to transfer this way and then go up, right? So you want to minimize the resistance that the current have to go through laterally. So by putting the buried region with higher doping, you basically reduce the resistor. So the collector can easily go through this one and then get collected vertically. Okay? But we don't have that in CMOS. So no matter how you look, this is a very crappy PMP. You can make it, but it's very crappy, not very good. So how poor? Normal PMP, you can get about 100 to 200 beta factor. Here, you probably only get 10 to 20, almost 10 times poorer. 10 times poorer. Next, you have actually large RB. Now, if you think about the normal BJT, because you use the N+, higher doping, the register for base region is actually very small. But here, you can only live with N-well. N-well is not high doping. So you actually have quite significant RB over there. Okay, so there is another drawback. So no good, no good. Another limitation, now BJT, you should be able to connect terminal to every way you want. So emitter, I can connect it to anywhere. Collector, connect to anywhere. Base, connect to anywhere I want. But this BJT, if you think carefully, the P substrate always has to be grounded, isn't it? For CMOS circuit, your P sub always have to be the lowest potential. Because if it is not, all your CMOS device is going to be in trouble. All the diode will be turned on. So the P substrate that are holding all the NMOS devices, the P substrate has to be ground. So in that sense, what you are telling people is like your BJT, the collector terminal, can only be grounded. You cannot put somewhere else. So these are another limitation. Now also, this one is more secondary. Alpha is actually the emitter or the collector current gain. Alpha equals to beta over beta plus 1. Okay, that is what it is. So this alpha actually also have high temperature coefficient. So let's look at the circuit. We have to redraw the circuit. Instead of having the BJT difference like something in front over here, like in this way, okay, now we have to redraw the circuit in this manner. Nevertheless, it will still be able to create VBE. Okay, so there will be a VBE over here. Okay, there is also another VBE over here. You can ignore the R. This is not something that we intend to put it. It's just there. Okay, you can ignore the R at the moment, and you will see that actually VBE1 will be applied across VBE2 and R. Okay, these two voltages are the same. So you can see that the VBE1 is equals to VBE2 plus IR. Okay, so we are still able to get what we want. So eventually your IR is still equals to VBE1 minus away VBE2. Okay, still the same thing. That's good. And you are still doing the same thing. Try to make the transistor Q2 A times larger. A times larger. So you are still doing the same thing. Now, here there are some minor difference. First of all, instead of having the emitter connected in this manner, what you have is you are having collector connected at the bottom. Okay. Secondly, this RB is always there. You cannot get rid of it because once you have the BJT, RB is there. Because you cannot directly connect to the base terminal. You have to connect to the N plus region, which will connect to the RB before you connect it to the BJT. So this RB is always there. So if you try to derive the VBE, so now your VBE will not be simple this guy. Will not be just simply this guy. Okay, your VBE actually, this is your VBE. So you will include the IR drop across the RB and then plus this guy, the internal transistor over here. So the internal transistor is given by this one, which is VT ln IC over IS. Okay, IC over IS. But unfortunately, you are not having IC over there because you are forcing the current to be equal on the emitter side. So you are actually forcing the emitter current to be equal. Okay, and because of that, your IC will be equals to alpha I naught, which is alpha IE. So that's why I have an alpha I naught over here. The formula has to use IC, but you are using the current mirror to force the emitter current to be equal, not the collector current to be equal. So therefore you have this alpha factor over there. And then over this guy, which is the additional voltage drop across the RB, which is simply given by I naught divided by beta, or should I say I naught divided by beta plus 1. Because we are actually, I naught is actually the IE, right? So therefore it should be I naught divided by beta plus 1. And then you multiply by RB, that will be the voltage drop across the resistor. So Compared to the previous one, we have VBE equals to VT ln IC or I naught over IS. So you will see there is some subtle difference. First, you have this additional term. Secondly, you have this alpha term. Okay? So to design the band gap, you can still use this guy to design the band gap, but now there is some limitation. In order to make sure that this error doesn't matter, you try to make sure that the current is actually very, very small, in microampere level. In that way, this guy becomes negligible. You are still dominated by this guy. Okay, so that is one of the way to take note in this CMOS band gap design. CMOS band gap, besides having the transistor, okay, there are people don't want to use the current mirror. Okay, they use the op-amp to do that. So this is a very popular band gap reference. So here you can see we are using the op-amp to force that these two voltage to be the same. Let's ignore the VOS at the moment. The property of op-amp is basically virtual short. Virtual short means that the V negative approximately equals to V positive. So you are forcing these 2 points to be equal, which is nice because this guy actually have VBE1 or VBE2. This guy actually have VBE1. So you are forcing VBE2 to be equals to VBE1 plus the current multiplied by R. So again, you are actually creating the VBE voltage difference. So your IR1 is equals to IR is simply given by the terminal voltage. Now, with the offset voltage of the op-amp, okay, with the offset voltage of the op-amp, if you consider this current, let me see. Okay, this is the voltage difference across the resistor. So IR1, this is the IR1 over here. IR1 over here. This is simply given by VT ln A. How do I say this? Okay, maybe I just right away do this using KVL, easier. So if you include the offset voltage, you are going to have VBE1 plus IR plus VOS, and then they will be equals to VBE2, right? So therefore, your IR will be equals to VBE2 minus VBE1 minus VOS, and then divided by, move the R over, divided by R. And this guy will be exactly this guy over here. Okay? So now, once you get the IR1 or IR, you can actually create the voltage. Okay? The voltage is simply given by your VBE2 plus the IR drop, which is IR1 multiplied by R1, which is this guy over here. That will be equals to your VL. Okay? This is simple KVL. Your VL is simply the voltage drop of this, and then the VB of this. Straightforward. So these two over here. Now if you expand it, you get the following. Now here, of course, you can expand the VBE2, which is VG0, okay, minus K1 VT. Sorry, not K1 VT. It should be K1T. So K1T, and then plus R1 over R, VT ln A minus VOS over here. Okay? Now, if you ignore the VOS at the moment, you can select R1 and R so that the two temperature-dependent terms cancel each other. Okay? Unfortunately, if you do that, usually R1 is bigger than R. Because R1 bigger than R, you will notice that the offset voltage also get amplified by this factor, because you are going to have VOS multiplied by R1 over R, based on this term over there. So this band gap reference have some advantage. First of all, unlike the current mirror kind of thing, you are going to have 3 BJT, right? But this guy is reusing Q2. And therefore it saves 1 BJT. This is nice because we already know BJT is not good. If it's not good, why create so many of them? Just create 2 of them and reuse. The only problem is that if your op-amp actually have offset voltage, you are going to amplify by this factor. Okay? So that is not good. Then that brings us to the very famous guy, Brocault cell. So this Brocault cell basically solved the offset amplification issue. Unfortunately, this is not applicable for CMOS. You know why? Correct, it requires NPN. CMOS only have the parasitic PNP, so you cannot do that. But this Brocault cell still worth understanding. So here, you have the 2R2 connected to VDD. Okay? So your IR1 basically consists of these 2 currents. So you can see it consists of emitter current from Q1 and emitter current from Q2. And then your emitter current from Q1 is actually equals also to the current across the resistor over here. And this current is basically given by, if you look at it, is basically still the difference between the BJT, base emitter voltage difference, across the resistor. So you still can get this term nicely. Okay? Now your IE2, this current over here, is simply given by the current IR, subtract away the VOS minus divided by R2. So how do we get this? If there is no VOS, this will be IR1, IR. This will also be IR, right? Because virtual short, these 2 terminals will have the same voltage. So the 2 currents should be equal. Now, this voltage, due to the offset voltage, this voltage is going to be higher by VOS. So which means the IR2 is going to be equals to the IR1. Sorry, not IR1, IR. Subtract away the additional voltage difference, VOS, divided by R2 over here. Because this is the current over here across the R2. Did I explain it clearly? If you consider, let's say this is VA, this is VB, okay, this is VDD. So IR is given by VDD minus VA divided by R2. Agree? Okay, and then let's call this guy IA, this guy IB. Okay, so this is IA. Now your IB is equals to VDD minus away VA plus VOS divided by R2. Right? So you are going to get VDD minus VA divided by R2 minus away VOS divided by R2. But what is this guy? This guy is IA. But what is your IA? Your IA is actually IR. So VOS minus R2. Okay? So you can derive this in this manner. Okay. Once you get all the current, let's look at the output voltage. This is what we want. So this output voltage, again, you try to reuse the BJT because this output voltage is basically this BJT plus the voltage drop across this R1. So you can see that your output voltage is simply VBE Q2 plus the IR1 multiplied by R1. But what is your IR1? Your IR1 is actually 2 times. What is your IR1? Yeah, IR1 is this guy. Okay? So if you sum them together, you're actually getting this guy over here. Because it's IE1 plus IE2, right? So it's basically this guy plus this guy. So you're going to get, let me write it out. So this guy also equals to VT over R ln A minus away VOS over R2. So if you have IE1 plus IE2, then you are going to get 2 VT ln A divided by R, and then minus away VOS over R2. Okay, so basically I just sum this term and this term together and I get this guy. So IR1, if you put this guy in, you are going to get 2 VT ln A over R minus away VOS over R2, and then you multiply by R1. So if you do this, you are going to get 2 R1 over R VT ln A, and then minus away R1 over R2 VOS. Of course, the VBE, you can substitute VG0 minus away K1 T plus this whole thing. So now your goal still doesn't change. You want to cancel this guy and this guy. But you can do that by simply manipulating R1 and R. R1 and R. But your VOS, although it depends on R1, it doesn't depend on R. It actually depends on R2. So it actually gives you a freedom. It gives you a degree of freedom. After you optimize, cancel away the K1 coefficient. So after you fix the R1 already, so you will choose R1 bigger than R. But you are able to choose R1 smaller than R2 because it's totally independent. So after you fix this guy, cancel already, you are free to choose any R2 that you want. And your goal, just make R2 to be smaller. And the good thing, now the offset voltage can actually be made smaller. So although the op-amp offset voltage is not small, maybe 10 millivolt, but if I choose R2 to be 10 times of R1, I can make it to be only 1 millivolt. Okay, so that is the Broca cell. Now, constant GM biasing, beside the band gap, which gives a temperature independent voltage, beside the supply independent biasing, where it doesn't matter what is the supply voltage, the current is always constant, there are need to create other kind of biasing. So constant GM biasing is one of them. If you think carefully over here, look at this guy. So what we are trying to do, we are using MOSFET to create virtual short. So the voltage at this point is exactly equals to the voltage at this point. So in the design, we are making M1A to be very big. And you learn this in high swing cascode. By making M1A very, very big, you are making the VGS for M1A to be almost equals to VTH voltage. Right? There is a nice little trick over there. So then the VT, which is the positive terminal voltage, will be simply given by the VGS M1 subtract away VGS M1A. And the VGS M1A is simply the threshold voltage. Okay? So you get this guy over here. Due to the op-amp, you are trying to force the V positive equals to V negative. And this V negative is simply given by IR over here. Okay? So now the top current mirror are forcing ID2 equals to ID1. And ID2 equals to ID1 is simply governed by this square law equation over here. Let's manipulate this equation a little bit. We know that if ID equals to half mu n COX W over L VGS minus VTH square, then your GM is simply delta ID over delta VGS is simply given by mu n COX W over L VGS minus VTH, right? So let's split this guy. split this guy, you can see clearly that I can split this VGS minus VTH2 square to be, maybe I rewrite over here, half mu n COX W over L VGS minus VTH, and then VGS minus VTH. Agree? I can split the square term into two brackets, right? So far so good. What is this? This is simply this guy, which is GM. So we can put this thing over there, and what you left is only the factor of half and this additional VGS minus VTH. So that's how I get the second expression over here. This guy. Okay, and what is VGS M1 minus VTH? We just derive it. And then ID cancel because they are equal. So in the end, you find that the GM for the M1 is exactly inverse proportional to the R. So this technique allows you to accurately define the GM. Previously, you only know GM is a function of current. But by designing it this way, you can define the GM to be exactly the factor of R, 1 over R. Okay? And to be frank, if you then bias this current to another transistor, this transistor also have the GM that is proportional to R. It's very simple to understand because GM depends on I. So now if I use the same I, right, and I already showed that this transistor M1 actually have the GM that is inversely proportional to R. If the other transistor also follow the same I behavior, they should also have the same characteristic of the GM. So in this way, you are able to bias the GM throughout every circuit. And what is the beauty for this one? So for example, let's say somehow I use this guy, okay, to bias this current, and then to bias this common source amplifier. Okay? So let's call this guy MA. So this transistor, I can be assured, will have the GM that is equals to 2 over R. Now, common source amplifier, what is the gain? The gain is given by GM R. So now your GM is already 2 over R. So you multiply by R. So the gain will be constant 2, totally independent of the transistor. You get the point? Of course, I don't have to pick R. I can pick 10R. So by using this circuit, now you are able to make the gain that is only a ratio. So in that case, the gain can be actually controlled quite accurately using this manner. There is another very important concept called reciprocal biasing. Okay, the concept shows like this. Reciprocal biasing usually involves this concept called master and slave. So if you bias the master in this manner using feedback, now if you apply this same biasing to other circuit which is identical, then this circuit will actually behave the same way as the master. That is what we call master and slave. So it's like you use the master to control the pupil, the slave. So if the master behave that way, slave have to behave that way. So let's look at this circuit over here. What does this circuit do? If you think carefully, one side is actually tied to VDD. The other side is tied to lower voltage, less than VDD. So very obviously, the current will always flow in this manner. Okay, because the right-hand side is actually turning on. So this current will flow in this manner. Now, if the current flow in this manner, then when the current flowing, you have voltage drop across this guy, and this voltage drop, you are going to force it to be equal to Vref. Okay, you force it to be equal to Vref. So this circuit is a static circuit. It just tells you if you have a differential pair, if you bias it this way, so when the voltage, the current sweep to one side, the other side voltage is fixed at Vref. That is what it is. Now, if you now use this same voltage to bias another differential pair, what this guy is doing is like, now the master, this is the master. The master already tells you, if you have this differential pair, if the current switch to one side, that one side voltage drop, the lower it can go is only Vref, because you use the master circuit to control it. Now if you apply the same voltage to the other differential pair, which is identical, exactly identical, M3 equals to M3, M4 equals to M4, the MIP, MIN, M1, M2 also equals to the master, M1, M2. Then when the differential circuit switch, you can be assured when you switch, when the voltage drop, that voltage cannot go below Vref. It's always stuck at Vref. Okay? So the idea is very simple. Consider twin, right? Consider twin. Or can you consider it as quantum entangling, something like that? Very similar. It's like you have two guys. They are related, right? If this guy behaves this way, this guy is identical, he has to behave this way. Okay? It cannot go totally beyond the control. That is the concept of reciprocal biasing. Now, this circuit is actually very useful in the delay lock loop design. So actually you can see they actually use it to design a ring oscillator. So this is delay cell. So you can actually use the delay cell to create a ring oscillator, something like that. But to control the ring oscillator, you want to make sure that the voltage is always well defined. So using this reciprocal biasing, you are able to control that the swing is always well defined by this. It can only swing between Vref and VDD. That is the master-slave design. Reciprocal biasing concept. It's not just applying here. A lot of circuits use this kind of master and slave concept to define the delay, to define the behavior of the slave circuit. Let me push a little bit more. The unity gain frequency, or we call FT, okay? This is a very important device parameter. If you look at any technology, the first thing we look at is the FT of the device. Okay, if the CMOS FT is 100 gig, then you know, okay, the circuit I design, usually I can make it operate comfortably up to 10 gig, 110, right? So if the FT is 100 meg, then I know I can only design comfortably up to 10 meg. There's always rule of thumb of 110. So FT is actually defined in the way that is current unity gain. You are measuring the output current over the input current, this gain ratio, and at what frequency this gain, current gain, drop to 1. That is how we define the FT. So you can use this simple circuit to define. At low frequency, you don't have any capacitor component, so you only have this guy. But you know you can add in parasitic capacitance at high frequency component. For example, you have base emitter junction capacitance, we call CI. We have the base collector junction capacitance, we call C mu. We also have the collector to substrate capacitance, so we call CS. For this simplicity of analysis, let's ignore C mu. Let's ignore CS. So we only have CI. Not too wrong assumption, because if you look at the BJT, the dominant capacitance will be the CI. Okay? Because this actually consists of the base emitter junction and also the diffusion capacitance of the BJT. So usually CI is quite dominant. Now then, if you derive the equation, you will notice that the input current is well defined by the input voltage divided by the impedance. So the impedance is simply given by SCI, sorry, not impedance, admittance, SCI plus the inverse of RI. Okay? And then you multiply by the VI, that will give you the input current. The output current is relatively easy. The output current is simply given by the dependent current source, GM, multiplied by VI. Okay? Let me see. Okay. So now, your VI, sorry, let me see. What am I getting at? A bit confusing. Okay. So I naught equals to GMVI, but you can have this relationship over here. So it becomes GM multiplied by II divided by SCI plus 1 over RI over here. Okay? So then you can rearrange, move this guy to the other side. That is how you end up having this expression over here. Now, if at high frequency, this guy is going to be much larger than Ri. So at high frequency, you have J omega Ci is going to be much, much larger than 1 over Ri. That is easy to understand because frequency is high, right? Ri is constant. So of course, with higher the frequency, this guy is going to dominate. Then you can ignore this guy over here. And then if you rewritten whole thing, you are going to get J omega Ci over GM, okay, equals to II over I naught. Or you can put it the other way, I naught over II equals to J omega Ci over, GM over J omega Ci. Okay? So, unity gain frequency is when the frequency such that I naught over II equals to 1. So if you do that, you'll find that the omega t is simply given by GM over Ci. And of course, if you want to look at the frequency in terms of hertz, you just divide by 2 pi. So this Ft, eventually, all this derivation tells you, if you want to get a good Ft, based on this expression, there are 2 things you can do. Increase the GM, reduce the Ci. And that actually has been the principle all along for technology. If you think carefully, CMOS technology gets advanced, so Ci drop. Right? Because the device gets smaller, Ci drop. So with Ci drop, your Ft is moving from 10 gig to 100 gig to even now terahertz. Okay? Another thing, if you want to get higher Ft, you boost the GM. But the GM is related to current. GM is related to current. So in the BJT cases, it's related to collector current. So that's why a lot of time in circuit design, you see that if you want high speed, pump more current. The higher the current, the higher the frequency. Okay? So these are the principles using this equation. You can illustrate what is the trade-off. I'll do a stop here, and then we can resume at 7:50. Is that fine? 7:50. Let's stop here. I still have quite a number of slides to cover. Any question?
Recording in progress.
Okay, let's do some quiz. Can you please scan the QR code? Okay. Remember to rank the supply independent biasing. The parameter should be very well known and more or less constant. So if you look at the variable and then you think that I cannot tell what is the value, it shouldn't be a good parameter. Okay, sorry, it's done already. Okay, VGS definitely is not good. So actually, for this question, you can use a rule out method. You see that VGS can never be good. Why? Because VGS, what is the defined value? How do you know? You don't know, right? Unlike VBE, you know it's 0.7. VZenner, you know it's breakdown voltage. right? And then VTH, you can easily use like the threshold voltage of the transistor, okay? Although you don't know the value, you know it's constant. Now band gap, that is definitely the best, right? So if you use the rule out, you know that VBE, V0, VBE as the first one cannot be correct, okay? For Bruker cell, all done? I don't know whether I make a mistake for this question. I think the second one or the third one all can be used. I think I make a mistake for this one. Okay, so if your answer is the third one or the second one should be considered correct. Should be considered correct. The first one, it cannot be used for all CMOS process we already go through because the Bruker cell require NPN and it requires the transistor to be floating. Okay, now CMOS with deep and well, usually it means that you are able to fabricate floated BJT over there, so that can be used. Now, BiCMOS is quite obvious. It can supply the BJT, so that one can also be used. The last one is suffer from offset voltage, but don't forget, it's able to reduce the offset voltage effect. So actually, it doesn't suffer a lot. In fact, you can choose the R2 to be very big that the offset voltage eventually is negligible. Okay? Let's resume. So we just now talk about the FT. I think the MOSFET follow quite similarly. So if you go through this low frequency model, for high frequency model, you're going to have gate drain capacitance, gate source capacitance, and drain body capacitance. Again, this is usually small. This is small. CGS is dominant, right? That can be well understood from the MOSFET structure. So in that case, if we derive the whole thing, the output current, so you can see that the input current II is simply given by the input impedance, which is the capacitance, multiplied by, the admittance, multiplied by the input voltage Vi. And then the output current, if you assume this resistor to be big, so the current is negligible, then the output current is simply given by GMVI. Okay, and then you equate, try to make the VI replacement. So eventually you go through the same analysis, you will see similar expression. The MOSFET FT devices is also depend on GM over CGS. So again, advanced technology reduce CGS. And if you want higher operating frequency, pump the current. Okay, pump more current. Now here, to simplify the analysis, usually amplifier consists of many stages. So if there is many stages and all these stages input output not linked, meaning that you don't have something feedback or something feed forward. Like here, very simple. Now to estimate the bandwidth is actually quite straightforward. Okay, you just have to look at every node. What is the associated R? What is the associated C? And then you can then form the pole simply by multiply the C1, R1 together. That will becomes the pole. Okay, in fact, the pole is actually 1 over C1, R1 because that will be the radian per second. C1, R1 is the time constant, but inverse of C1, R1 becomes the pole. So then you can actually have this isolated pole and written out in a very simple manner. So that is the key. If the input and output of the node are not associated, this can be easily done. But if you have something that link the two together, okay, it doesn't have to be series. Sometimes it could be this kind of thing. Okay, when that is happening, then the analysis is not that straightforward. Okay, it's a bit complicated. So here, let's assume, you see, this is already feeding back from one side to the other side. So here to analyze it, we assume C mu to be negligible, so there is no feedback. In that case, we just have to look at what is at this point, what is at this point, And at this point, very easily, the output resistance is simply given by RL1 parallel with RI parallel with R0. Okay? Of course, if you choose RL1 to be dominate, then the whole thing becomes almost like RL1. Okay? And then the capacitor is simply dominated by this guy because it's the CI of the next stage. We already say the base emitter capacitance is the dominant one. Here, you are going to see the collector to the, what is the capacitance? Let's take a look at this guy. Yeah, CCS, collector to substrate capacitance. So if you only look at Q1, there is a collector to substrate capacitance, which is negligible. So we can assume CI to be dominate. So in that case, the dominant pole per stage is simply given by CI multiplied by these two resistors in parallel, RL parallel with RI. We assume the R0 to be very big, so we can ignore it. And if you further choose RL1 to be smaller than RI2, then the whole thing is dominated by this guy. Now, usually RI is not big, very big. It's usually in kilo ohm. But here we are talking about RF amplifier. For RF amplifier, because of the wide bandwidth, we are not talking about baseband amplifier. We are talking about RF amplifier. If it is very wide bandwidth, the load resistance usually is in terms of 50 ohm, 75 ohm, right? Or even you want a larger gain, maybe 100, 200 ohm. It will not reach kilo ohm range. So in that sense, it's not surprising the whole resistor is going to be dominated by RL, the load resistor, because it is usually small for RF amplifier. Okay? Now, here we define a term called gain bandwidth product. So gain, we already showed. Gain is simply this guy. Now, bandwidth is given by this guy. So if you multiply them together, okay, you have GM2, RL2, multiplied by bandwidth, which is this guy. So eventually, if all these load resistance, you choose them to be about the same, eventually the gain bandwidth product is given by this guy, which is related to your unity gain frequency. Okay, so that actually shows you the maximum frequency that you can actually achieve for the RF amplifier is also somehow related to the unity gain frequency, FT. Now here, show you the important thing about the gain bandwidth product. Now gain bandwidth product is basically when the gain drop to unity or 0 dB or unity. That frequency, when the gain drop to unity, is what we call gain bandwidth product. Or in another word, you can also find it by simply multiply the gain with the 3 dB bandwidth. Now this is only true for single pole system. For single pole system, you multiply the gain with the bandwidth, you're going to get out the intercept where the gain drop to unity, that frequency. They are the same thing. So this guy is exactly the same as the gain multiplied by this guy. This is true for single pole system. Okay? Now, knowing GVW actually can add as a very useful rule of thumb. So we already established the GVW is somehow similar to omega t or Ft. Okay? When you design amplifier, you would not design amplifier up to this point. Am I right? Because you don't have any gain. If you design something without any gain, what is the use of it? So usually you try to design something useful, maybe 20 dB. 20 dB is a gain of how much? 10. Right? If it's gain of 10, it means that it can only operate up to Ft divided by 10. Because gain bandwidth product, you are trading off the gain with the bandwidth. So if you want to use out the whole frequency, you can only get 0 dB gain. But if you are able to sacrifice the bandwidth by 10 times, you are able to gain up to 10 times. Right? So that is the gain bandwidth trade-off. So that's why a lot of time, if we simply look at the Ft, we can sort of determine what is the useful range of the circuit. Okay, so for example, if let's say BJT, it tells you the Ft is 10 to 20 gig, then you know that the circuit is probably useful up to 2 gigahertz. okay? Or if it's 0.35 micron, 10 to 20 gig, same thing. You try to design circuit up to 1 to 2 gig. And then for gallium arsenide, 50 to 100 gig, you can design circuit up to 10 gig, for example. Okay? You probably, if you are in the IC design, you look at all the reported paper, sometimes you will see the FT for some technology is 60 gig, but yet people are designing circuit probably close to 60 gig. That can happen, because don't forget, in RF we have what other component? Inductor, right? Inductor can do what? Inductor is a positive reactance. It can actually resonate out the parasitic capacitance, right? So in that case, you can actually establish or extend the bandwidth further. Okay? Now, effect of parasitic resistance. So let's look at this simple common source amplifier. So again, we do the same thing. Assume CGD and CDB negligible. The dominant one is CGS. So bandwidth per stage. So beside the bandwidth per stage, we look at this node. Beside the load resistance RL1, we are going to have this additional gate capacitance, gate resistance. So this resistance becomes RL1 plus RG. It's no longer RL1. And the capacitance is still the same, the gate to source capacitance. Now for the gain, you can still consider it's dominated by RL2, so the gain is still the same. Now if you try to figure out the gain bandwidth product, so you multiply the gain with the bandwidth, you end up having the following. And you notice that this is different from the previous stage without the RG, okay? So compared to the previous stage, you have a factor that is less than 1. So let's consider this factor alpha. So alpha is actually less than 1. Okay? So it shows you, because of this RG, your gain bandwidth product is probably going to be smaller than the unity gain bandwidth that the amplifier can achieve. So RB and RG is actually very critical in the high frequency operation. I believe I covered that last week. Okay? I show you, if you simply design, so for BJT is quite straightforward. So let's assume here you create multiple finger, so the emitter will have multiple finger. Your base also got multiple finger. You don't have to do that. You can just create one emitter and then one base over here. You can do that, right? But instead of doing that, you can use the interdigit finger. So by doing that, what is the advantage? It is like you are having multiple BJT connected in parallel. And by doing so, you are splitting the register RB in parallel to the different transistor. And the good thing is that not only you make the RB smaller per finger, beside this guy, you actually make it smaller due to the parallel combination. So the advantage is not just simply cut by linearly, it actually cut by square. For example, if you cut from 1 finger to 4 finger, you are not reduced by factor of 4. You are reducing by factor of 16. Why factor of 16? First of all, the register reduced by 4 times. Now this 4 register connected in parallel, it reduced further by 4 times. So altogether, 4, it actually reduced by 16 times. Now this example illustrates very well. If you design a transistor MOSFET with 100 micron over 1 micron, so 100 micron is too big. It's not good for RF design. So usually for RF design, you try to limit the width, finger width, to probably less than 10 micron, maybe 5 micron. Okay? At very high frequency, people even suggested keep it down to 2 micron and below. So here, just an example, if I keep it to 25 micron, so I'm already reducing this finger by 4 times. So each of them will have 4 times smaller register. Okay, so your RG1 originally is having 500 ohm, sorry. So 5 ohm per square, you have 100 square, so 500 ohm. Now because I cut down the finger width to 25 micron, so right away I'm reducing it from 500 ohm to 75 ohm. Oh, sorry, not 75, 125 ohm. So you reduce the register by 4 times already. But not only that, because you connect the register in parallel, you have this additional factor. So altogether, you are reducing from 500 ohm to 31 ohm, which is reduced by a factor of 16. Now, let's start looking at C mu and CGD. C mu is small, yes. But what if we purposely add in a feedback capacitor, CC? So the reason we call it CC, the C, subscript C, stands for compensation. Okay? By adding this capacitor, you actually can achieve sort of phase margin improve. We'll cover that later. But right now, let's take a look at what really happened. So, still the same model. You have the RL1 from the first stage. You have this C1 due to the gate source capacitance of the MOSFET. And then you have the current source. You have the RL2 due to the second stage. And then same thing, the additional capacitance due to the second stage gate source capacitance. And then we have one capacitance linking the first stage output to the second stage output, CC. Now to derive this one, you have to go through simple KCL. Okay, so I'm not going to go through it. So basically you look at NOT 1, which is this guy. You look at NOT 2, which is this guy. And then you try to sum all the current equals to 0. That is KCL. And after some manipulation, you are able to find VI over VI, which is this formula. Very complicated. So I'm not going to bore you down with the derivation. And although this looks simplified, but if you look at the coefficient A, it looks something like this. If you look at the coefficient B, it looks something like this. Okay? Very, very complicated. Now, for the pole, I know this is second order transfer function, so I'm going to have two pole. If you are able to factorize them, you are going to end up having two pole. The 0 is simple. The 0 is only the numerator, so the 0 can be determined easily as GM2 over CC. Now this is algebra derivation, very, very tedious. So I'm going to look at this in a different manner, so which allow us don't have to derive, don't have to memorize a lot, and we are able to right away see what is the two pole and what is the 0. Okay? So let's consider the case 1 when you don't connect the CC, which means the first stage and the second stage, they are isolated. Okay, there is no CC. So if that is the case, we already know the result. If there is no link, then the first pole will be simply due to the first stage. What is the resistor, what is the capacitor? You can determine. The second pole, also very clear cut, is going to be associated with the second stage resistor and the second stage capacitance. So this is very clear cut. And there will not be any 0, because you are not linked, then you only have the pole. You don't have 0. So this is straightforward. We don't have to use the derived equation before. This we have done it earlier when they are isolated. And what you have, if you look at the pole 0 diagram over here, as planned, this is the imaginary axis, and then this is j omega, and then this is actually the sigma axis. Okay? So if you look at the pole 0 diagram, you are going to end up having two pole, P1, P2, and these are real pole, okay, determined by this guy. Okay? And then the 0 happened at infinity, so actually you don't have to draw anything. Now, when the capacitance start to be introduced, so you try to introduce non-zero capacitance inside. Okay? What you are going to see is that the pole start to split. Okay? Starting from here, if you increase the C, you will see that one of the pole will move closer to the j omega axis. One of the pole will move further from the j omega axis. We call this behavior pole splitting. Pole splitting. So the effect of introducing the CC is basically introducing pole splitting. Also, you are bringing in the 0 from infinity down to something finite. Okay, so that is the effect of introducing CC. Qualitatively, that is what happened. So just remember that. Now, if CC is so large, if the CC that we introduce is so large, the two poles get far separated. So one is very small because close to j omega. Another is very large because close to infinity. So you can see this guy over here. Then we can actually derive the two poles in a very easy manner, because let's say this is the pole. If you multiply them, you will know that this is actually the sum of the pole. This is the product of the pole, right? You know this from simple algebra. Now, if one of them is very, very big, then actually you can ignore the sum of the other term. So actually you look at the polynomial, you can right away derive the first pole. You don't even have to factorize the polynomial. If you make the assumption, due to the introduced CC so big, the two poles separated very widely, so one of the pole is going to be dominate. In that case, the sum of the two, one of them is going to be very big. I can ignore the other. So simply looking at the final derivation, which is this guy over here, once I find the A, that becomes my first pole, right? Very easy. And then once I determine this P1, of course, looking at the coefficient of the second one, of the x squared, I already know the P1. I just have to divide the coefficient by P1, I can get P2. Get the point? Okay? So this illustrates the principle, how you can actually easily derive the result. So the first pole is simply equate to, the previous slide. So from this result, we can equate 1 over P1 equals to A. Right? And then how do you get P2? We will get 1 over P1, P2 equals to B. So therefore, 1 over P2 equals to B multiplied by P1. This one allows you to determine P1, this one allows you to determine P2 in a very easy manner. Okay? So the first pole, we already derived this guy over here. It looks very, very complicated. But if we analyze this equation, we find that because of this GMRL, that is the gain. So all the other you can see is simply RC, RC, right? But this guy has RC multiplied by gain. So if all the capacitor is around the same order, all the resistor is around the same order, then the third one, beside the same order RC, are actually amplified by additional amplifier gain. So I can safely assume maybe these two is negligible. Only this one dominate, and I can get this guy. So the first pole can be simplified into this equation over here. Bear with me, I still haven't teach you how to actually look at this guy without memorizing it. It will come later. And then for P2, so we make use of the product coefficient, and then we know the P1, we substitute it inside, and then eventually we derive this whole expression over here. Okay, this whole expression over here. So if the CC is big enough, because that is our thing, right? We say CC is large. Okay, larger than C1. That is not surprising, because if you look at C1, C2, they are the parasitic associated with transistor. CC is what we introduce purposely. So we can actually purposely make it large. If that is the case, then of course I can ignore this guy. And then RL cancel. Okay, let's look at what we are going to end up having. CC also cancel. We end up having this guy over here. And that is our second pole. So far so good. So this guy is our first pole, this guy is our second pole. It looks simple, but you still have to look at this equation, and it doesn't make sense, right? But let's see, how do we link this equation to what we are going to see in a very easy manner? We have introduced about Mueller effect. So for Mueller effect, if there is an amplifier with gain of minus A, and if you have a feedback capacitor C, then you can actually reflect this capacitor to the input side. You just have to make the capacitance 1 plus A times larger. Okay? So let's look at what happened. We introduce CC. Once we introduce CC, if we use the Mueller theorem or Mueller effect, we amplify this CC by the gain, which is 1 plus GMRL. Right? This is the amplifier gain. Then it will appear at the input side as follows. Now, we have successfully get rid of the feedback CC. We are reflecting the CC into the input side. What is the total capacitance? C1 plus this whole thing. But of course, this is big, so I can ignore C1. Right? So I'm going to get C1 plus this guy multiplied by this resistor, RL1. And if you assume 1 is negligible, C1 is negligible, you will get exactly this value, which is what we just simplified, right? So do we have to go through all the derivation? We don't have to. You just need to know what is the CC, and then you just need to know what is the amplifier gain. You amplify this CC by the amplifier gain, and then you multiply by the resistor seen at the input side. Your job is done. So no need derivation. So we go through all these troubles showing you the exact derivation. We go through the simplification showing you how this guy simplified into this guy. And finally, we use Mueller effect to show you, actually you don't need derivation. They are the same. So therefore, you don't have to memorize anything. Next time, you see this guy, the first pole, use the CC, multiply by the amplifier gain, and then you multiply by the input resistor. That's it. Your job is done. This is how you determine the first pole. How about the second pole? The second pole, we get this result. But can we derive this result in a very easy manner? If you think carefully, at high frequency, second pole happen at high frequency, right? Second pole is the non-dominant pole. It happened at high frequency. Now, if it happened at high frequency, the CC, due to the large value at high frequency, CC probably behave like short circuit. Am I right? So replace CC with short circuit. Now, C1, C2 you cannot because they are still small. You have CC much bigger than C1 and C2. The impedance is 1 over j omega CC. This is 1 over j omega C1, 1 j omega C2. Since this guy is small, so when the CC go to 0, these two not necessarily go to 0. Am I right? Okay? So then, having this guy short circuit, let's look at how can we derive this easily. This is diode connected transistor, so I can replace it with 1 over GM. No issue, right? Yes? Okay. Now, RL1, RL2, the two resistors in parallel, so no issue, right? Okay. Now, one side you see C1, one side you see C2. Now, if we assume this guy is actually small, then you can ignore RL1, RL2. So basically, the pole is what? The pole is simply 1 over GM2. So 1 over GM2 multiplied by the two capacitors, C1 plus C2, which is exactly this guy, isn't it? Right? So it tells you another simple way of deriving the non-dominant pole. So you assume frequency so high, the CC behave like short circuit. Then what you have is basically transistor becomes 1 over GM. And then the total RC is basically one side C1, the other side C2, multiplied by the total resistor, which is dominated by 1 over GM. And then you get this second pole easily. Get the point? Okay. 0. How do we derive 0? Just now we go through all the trouble. Summing the current and not 1, not 2, equate them, we derive the algebra. We have shown you, you don't have to do that. You can easily obtain pole 1, you can easily obtain pole 2. But how about 0? So what is the definition of 0? 0 basically means when S equals to Z1, output equals to 0. That is what 0 means, right? Pole is the other way. If S equals to pole, output go to infinity. Right? But for 0, if S equals to 0, output go to 0. Simple as that. That is the definition. So to derive it, you look at this circuit, output equals to 0. Okay, output equals to 0. Now, in AC analysis, this is also 0. So is there any current going through RL2? No, because two sides of the resistor is 0. So no current go through RL2. So what you have is basically this input current over here. Okay, so VI multiplied by SCC. And then equals to the current source, which is GM to V1. Right? So this guy, if you look at S equals to Z1, and then you cancel VI, so eventually you obtain this 0, GM2 over CC, which is what we derived earlier. Okay? So there is a simple way to derive the 0 instead of going through all the derivation and manipulate the algebra. Okay, body plot. I don't know how to pronounce this. Some people tell me it's bot plot. Some people tell me it's body plot. So I don't know. So you can pronounce whatever you want. I pronounce it as a body plot. Now, we want to know the body plot is because a lot of time, if you look at the transfer function, we want to know how the frequency response looks like, how the magnitude response looks like, how the phase response looks like. Okay, what is the dominant pole, what is the non-dominant pole, so on and so forth. So, of course, nowadays with computer, you don't have to do that. Okay, with computer, you can easily generate it. But I still find this thing useful because a lot of time, for example, I seldom do simulation nowadays. Right? I pick up the simulation because I need to teach you guys. Just kidding. I seldom need to do the simulation nowadays, but if needed, I can still do it. I assign simulation to my student, right? They have to design the thing, they have to simulate. When they report to me, how do I know they are doing the good job? I redo it again by myself. Is this very efficient? Your boss give you the job to do, so your boss want to verify you do a good job or not, so your boss redo himself. Does it make sense? It doesn't make sense, right? So you know what to expect. You ask your student to reproduce this thing to you. You quickly glance through. If you are able to look at this and make sense out of it, you don't have to redo the simulation yourself. Okay? So having this kind of basic understanding is sometimes useful. Right? It's like a lot of people do investment. They look at the stock market trend. They look at all these reports. They're trying to make sense out of it. They don't have to run the company to understand. But if they are able to read the report, they can make sense of it. So think of it that way. So to understand what kind of thing you are expected, so when a student produce this simulation result to you, how do you know that it is right? If it's two-stage, you roughly know, I got dominant pole, non-dominant pole, how should the phase response looks like? How should the gain response looks like? So to understand that, we need to establish some rule. All the transfer function, all the odd end eventually have transfer function. It just depends on whether it is second order, third order, or even higher order. Right? It depends on whether your odd end is two-stage, single-stage, three-stage, so on and so forth. So if it has transfer function, it has more than one stage, it definitely has pole or zero. Pole means it has S plus something at the denominator. Zero means it has S plus something at the numerator. So if a transfer function has S plus something at the denominator, pole, how would it behave? Now, if you learn about system, you know that for stable system, the pole can only be left half plane pole. You know that, right? I see some of you nodding the head. Do you just remember, or do you really understand why? Why it must be at the left, not the right? Why a stable system must be at the left, not at the right? Anyone? Come to this one. Now, j omega axis, if you have any pole that has j omega axis, you expect that the response will have this oscillation. This is sigma axis. If you have anything on the right hand side, you are expecting the signal to grow. Unstable, right? But if you have something at the left hand side which is negative, you expect the thing to be decaying. So for any stable system, it always has to exist in the left half plane. The pole has to be at left half plane. That is the reason. Now, so if there is a pole, let's say something like this, to figure out the phase, quite easy. A single pole will introduce minus 90 degree per pole. So if the system have one pole, you already know it will eventually introduce minus 90 degree. And beyond the pole, so every pole will introduce 6 dB, minus 6 dB per octave, or minus 20 dB per decade. Minus 6 dB per octave, it means that frequency double, gain drop by half. That is per octave mean. 20 dB per decade means gain drop by 10 times when the frequency increased by 10 times. That is all it means. Now, at exactly the pole frequency, it should introduce minus 45 degree. And exactly the pole frequency, it should introduce minus 3 dB magnitude response. Okay, so that is the pole. Just bear with me. I know all this description is kind of dull or dry, but after we go through this, you will see how we are going to plot. So left half plane 0. 0 can be left, can be right, because it doesn't impact the stability. The stable system. So stable system can have left half plane 0 or right half plane 0. So we have to split them into two. But for pole, it's always left half plane pole. So we don't have to split. Now for left half plane 0, so when the 0 appear at the left hand side, now it will introduce positive 90 degree phase shift per 0. And then it will also have the response that is going up. Every doubling of the frequency increase the gain by 6 dB. Or every decade increase in frequency increase the gain by 20 dB. At exactly the 0 frequency, it will introduce positive 45 degree phase shift. And exactly 0 frequency, you will introduce positive 3 dB gain. And then for the right half plane 0, the magnitude response is actually the same as the left half plane 0. The only difference is like the phase shift. Instead of positive, it actually behaves like a pole, negative shift, negative 90 degree, and negative minus 45 degree. Now, let's look at in diagram, what does it mean? So if you have left half plane pole, let's say something like this, okay? So at exactly the pole frequency, you can see that this gain drop by minus 3 dB. Now, of course, we don't draw the minus 3 dB. So we just simply draw a straight line and then join at that pole frequency. But if you want to be exact, you zoom in that pole frequency, you will see that if you zoom in this guy, you are going to see something like this. So this difference is about minus 3 dB over there. And then at exactly the pole frequency, you see minus 45 degree. And the slope for this guy is minus 6 dB per octave or minus 20 dB per decade. For the phase, if the frequency is 10 times of the 0 frequency, then the phase flattens out to minus 90 degree. If the frequency is 10 times the 0 frequency, then the phase is actually 0 degree over here. So that is how you plot the phase response. For left half plane 0, where you use a circle to indicate 0 and on the left side. So same thing, at exactly the 0 frequency, actually if you try to plot it, although we use a straight line, but if you try to plot it, it will look something like this. There's a curvature. And this difference is about positive 3 dB. Okay? But we don't plot the curvature. We just use two straight lines to join at Z1. The slope will be 6 dB per octave. And this is also the same for right half plane 0. So the gain response looks exactly the same. But in terms of the phase response, at the 0 frequency, left half plane 0 introduced positive 45 degree. But right half plane 0 actually introduced minus 45 degree. Okay, so here we just start with initial 180 degree, so minus 45, it becomes 135 degree. The reason why that is doing that, I forgot to mention. So you look at S equals to 0, which is S equals to j omega, and when omega is very close to 0, this whole thing is actually minus 1, right? So because of this negative, so it has initial 180 degree phase shift. That is the reason. Okay? So you start at 180 degree, you drop 45 degree, you reach 135. And same thing, when the frequency is 10 times the zero frequency, it flattens out to minus 90 degree. When the frequency is 0.1 of the zero frequency, it's actually 0 degree. So you start with 180. So let's look at this. Suppose I give this job to the student, simulate this two-stage amplifier. Okay, you already simulate the whole thing. So by looking at all the small signal parameter generated, okay, you can actually predict. So a lot of time I tell students garbage in, garbage out in simulation. In simulation, garbage in, garbage out. This happens a lot. Okay, they design the op-amp, but when they simulate the AC response, it doesn't look like anything covered in the lecture. Okay, so the first thing when it doesn't look like anything covered in the lecture is to ask yourself, do I make any mistake in the simulation? So usually the first thing you do, you generate the small signal parameter. Of course, the first thing you do, you try to make sure all transistor is in saturation region. Am I right? Once it's in saturation region, you try to look at the small signal parameter for each transistor. This can be easily generated, right? This can be easily generated. And then now you can start analyze the first pole. So the first pole, we already say we don't have to derive. The first pole, this is CC, right? CC multiplied by the second stage gain. The second stage gain is GM6 multiplied by R06 parallel with R07, right? So you multiply by CC. And then you multiply by the total resistance at this point, which is R04 parallel with R02, which is this guy over here. So no need derivation, just use the Mueller. You can derive the dominant pole. And then from this one, you can deduce the dominant pole should be happen somewhere between 69 kilohertz. Okay? The non-dominant pole, we treat this guy as short circuit. And then there should be two capacitors connected on both sides. One side is CL, usually is big. The other side will be the characteristic of this transistor. I actually don't care because I know it's going to be much smaller than CL. So therefore CL is 10 pico. My transistor cannot be having picofarad, right? So in that case, my omega PL, although it is plus CGS M6, but this is so negligible, I ignore it. So eventually it's just GM6 divided by CL. I end up having 159 megahertz. The zero frequency, okay, is again the same thing, GM6 divided by CC. So you calculate, you end up having 400 megahertz. And the gain is 63 dB. The gain is easy. It's basically GM2 multiplied by R02 parallel with R04. And then you multiply by GM6 parallel with R06 parallel with R07. So that is the gain. You can derive this easily. So now let's look at the simulation result. So we do a sanity check. First we check, oh, the gain, is it correct? 63 dB. Oh, seems okay. This is the correct gain. The dominant pole, we derive 69 kilohertz, but from the measurement, it's around there, 63K. You cannot expect the calculation to be exactly the same as the simulation, because in calculation, we throw away a lot of things. But it's close, so that's fine. Right? There are some small error. At least you're not talking about, I expect 63, I expect 69, I'm getting 630, 10 times different. Then you will know something is wrong. Okay? If it's about the same order, that's fine. It means our calculation is close, so the result can be trusted. And the slope, if you notice, is actually minus 20 dB per decade. So we know, right, in gain response, after the first pole, it will drop with minus 20 dB per decade. And then the second pole, you can see probably the slope changes. Am I right? So this is more gradual, this is steeper. You can see that, right? It's not a smooth line. If you look carefully, it will be something like this. So the middle point looks somewhere around here, which is about 65 megahertz. Also close to what we are estimating, right? Not exactly close. We are estimating 150 something. So this is about 65, right? But still consider okay, quite close. And beyond this dominant, non-dominant pole, your gain start to drop at minus 40 dB per decade, which is what we expected. And then finally, we see that the slope start to change again. So initially the slope is like that, and then it goes steeper, and this have the trend of simping to go more gradual again. So what is this frequency? We know is the zero frequency, about minus 400 megahertz. So looking at this curve, we can sort of know, okay, it makes sense or not. Maybe it makes sense, okay, very close to what we are estimating. And do I need to carry out the simulation to double check? Probably not. I just need the student to generate all these small signal parameters. Of course, I make sure all the transistor is in saturation region. Okay? So therefore, in your design, there is always my request, please show all the device VDS set. Look at your homework 2. You better do that. Okay? VDS set. Why? Because I want to make sure in your design, transistor is in saturation region. And then after that, list down all the GM, all the R0, so that I can be sure they are correct. Right? Phase response. So if you look at the phase, see how we can apply our knowledge. So at exactly the pole frequency, you see, this is minus 45 degree. And then at the second pole frequency, you see that it dropped to minus 135. Right? And then finally, at the zero frequency, it dropped further by another 45 degree. So looking at the phase response, we can also sort of tell whether it is right or wrong. Now let's look at common source with source degeneration amplifier. So again, we don't care too much about this CGD because there are ways to reduce this effect. Remember we introduced about cascode, right? So in cascode, we are making the gain smaller, so the Mueller effect doesn't matter, right? So unlike the CC, we purposely want the CC to have Mueller effect, so we have dominant pole. Here, this is unintended, so if we don't want the CGD to impact us a lot, we can actually introduce cascode and then put RL over here. Then basically the effect of CGD can be made negligible because CGD is not being amplified. So let's focus our job on the CGS, which is the dominant capacitance here. Now here we are going to make use of reflection rule, the BJT. We look at this rule when we derive the LNA. So here is the same thing. If you look into the BJT Rx, according to the equation, the reflection rule tells you Rx is simply Ri plus 1 plus beta Re. You can expand this term and it becomes something like this. So basically Ri is having a register here, Ri. Okay, so we do a one-to-one mapping. Your MOSFET doesn't have Ri, but it has CGS, or I can call it Zi. So if BJT have this guy, then for MOSFET, I can actually have the same thing, Zi plus Re plus GM, Zi multiplied by Re. We learn about this when we derive the LNA with inductive degeneration, right? I'm still doing the same thing over here. Except that this Zi is actually 1 over S CGS. So here, after some manipulation, I find that the Zx actually becomes something like this. Something like this. In fact, I can treat this guy as having a capacitor that is actually divided by a ratio 1 over GMRE and then in series with RE. If you look at the expression, it's exactly what this guy means, right? If you look at this expression, If you look at this expression, you are having two resistors in series, RE in series with this guy. But for this guy, I can consider it as like a capacitance. This capacitance is given by CGS 1 plus GMRE. Agree? Right? So therefore, I can actually transform the circuit. Your input consists of RS, and then because of this CGD, due to this cascade, I'll amplify by 2 times. The gain is become 2. So therefore, the CGD will reflect at the input and show up as 2 times CGD. So that's why I add the capacitance over here. And then when you look into the gate side, you actually have this thing. We just derive it. Now, to derive the total bandwidth of this guy, what we can use is make use of some theory called open circuit time constant. So in open circuit time constant, what they describe, I'm not going to prove the theorem, but this is well known. If you have multiple capacitor, you want to look at the total bandwidth, what you do is you look at individual capacitor to determine the time constant, and then you try to sum all these time constant, and you inverse all these sum time constant. That will give you the overall bandwidth. So this is what we are going to do. There are 2 capacitors, so let's open circuit one of them. You end up this guy. And then later we open circuit this guy, we end up this guy. So there are 2 time constants you can get. The first time constant is easy, just RS multiplied by this guy. The second time constant is this guy multiplied by these 2 resistors in series, not in parallel, in series, because you are actually combining this ground together. So you see the 2 resistors in series. So therefore, the first time constant is this one. The second time constant is this capacitor multiplied by these 2 resistors in series. After you sum these 2 time constants, you invert them. And that will actually give you the bandwidth for this amplifier. Okay? There is common source with degeneration. Okay? So now, let's look at this guy with source picking or emitter picking. At very low frequency, this is open circuit. So what you have is exactly the common source with degeneration amplifier. So you are going to have a gain that is lower, this guy over here. Now if you don't add in the capacitor CE over here, you are going to end up having this structure. Okay, this structure. So the gain is like this one, and then the bandwidth, although we use the open circuit time constant, if we ignore this guy, because CGD is small, then the bandwidth is simply given by this guy. So we will have this amplifier structure shown over here. Okay? Now if you introduce the CE, what is going to happen is that at high frequency, CE behaves like short circuit. So you are transforming the amplifier from common source degeneration to common source amplifier. So you are transforming the amplifier from this initial low gain to the middle one that have high gain. Okay? The transformation started at this 0 frequency, which is very well determined. It's simply the RACE time constant inverse. Okay? And then when does it becomes flat again? It becomes flat at this point when you look into here, you actually see 1 over GM parallel RE. But at that frequency, it means that 1 over GM is actually much dominant compared to RE. So eventually it is just 1 over GM multiplied by the CE to get the register, the pole. And then the second pole basically is determined by, the omega P2 is basically determined by the output side over here. So for common source amplifier with this kind of source picking, you will see this kind of like band pass characteristic. Okay, there will be high gain at the middle band over there. Common collector, common base frequency amplifier is actually very similar to common source, common emitter. We derived already. So just repeated, except that the gain, you see, every stage provides GM, but every stage also see 1 over GM. So the gain is almost like unity. Okay? And then the bandwidth per stage, you are going to every stage dominated by 1 over GM, and then every stage also have CGS, and then you invert them. That's why you get GM over CGS. Okay? So the gain bandwidth per stage, you multiply the gain with this guy, you also end up having omega t. So it's very similar to common source, common emitter amplifier. Common drain, common collector amplifier. So at low frequency, we already derived the gain about this one, and it's actually quite close to unity gain, assuming there is no body effect. Okay? If there is a body effect, you will change to GM RE 1 plus GM minus GMB RE, which have less than unity gain. At high frequency, CGS will behave like short circuit. So in fact, what you have is simply a resistor divider, RE divided by the total resistor over here. So at high frequency, due to the short circuit provided by CGS, you just end up having a simple resistor divider. So to determine the frequency, we can use a similar thing. If you look at this guy, you will see that this thing and this guy, basically we derive similar to these cases over here, right? This guy and this guy, same cases. So we can use the same result that we had derived earlier. So you are going to see CGD, and you are going to see this capacitance in series with RE. Okay, the gain we already introduced. The bandwidth, we are using the open circuit time constant, so we determine this guy and determine this guy. If we ignore the CGD, it's basically just this guy. Okay. Now, to determine the gain bandwidth, we have this gain. We multiply by this bandwidth over here. We end up having this one. If it is negligible, so the bandwidth becomes the following. You see that it will still reduce into something very similar to omega t. Basically, I assume this guy to be dominant, so I can ignore the one. So what you have will be GM over CGS, which is omega t, and then RE over RS plus RE, it becomes a factor that is smaller than 1. Okay? So common drain, common collector also can have the bandwidth very close to the unity gain bandwidth with a factor that is slightly smaller than 1. So it looks something like this. Okay? At alpha GM over CGS, which is alpha omega t. Okay? The gain will start to drop. So the amplifier have the unity gain up to this bandwidth over here. And then at high frequency, this is unity. But at high frequency, you have this voltage divider. Okay? So therefore, at certain frequency, is going to be flattened over here. This is the zero frequency. And the zero frequency is determined as GM over CGS. Again, we didn't derive the derivation. We just basically assume. We didn't derive the algebra. What we do is that we know at 0, V0 equals to 0. So let's take a look. If V0 equals to 0, there is no current flowing through, so you can ignore this guy. So you have on top a current source, which is GM VI, right? Or GM VGS. Okay? And then at the input side, you are going to have VI multiplied by SCGS, okay, which is this guy. So the two has to be equal, and eventually you will end up having the zero frequency as follows. Now for differential amplifier, if we don't have any feedback, we can actually just determine, we can determine the pole separately. So here you identify two different poles. One is actually at the output. Another is actually over here. Okay? At this point. These are the two dominant pole, two significant pole location. Okay? So to determine the CX, you can see that it consists of CGS for the M3, CGS for the M4, and then the CDB, drain to body, for the M3, CDB for the M1, CGD, which is here, for the M1, CGD4, which is here, for the M4, but you need to consider the Mueller effect. So therefore you amplify by the gain. So this capacitance can be quite significant. That's why this is one of the potential pole location. And then another dominant pole location is due to this CL. This CL is going to see a huge resistance given by R04 parallel with R02. So this is going to be your dominant pole. Your capacitor is large, your resistor is also large. Now, this guy becomes your non-dominant pole because although the capacitance could be significant, Cx, but if you look at the resistance at this point, it's going to be dominated by 1 over Gm M3 because your M3 is diode connected transistor. So the resistor is actually not that big. So therefore, if you multiply together, you are going to end up having this one. So although capacitor could be significant, the resistance is not. So it becomes non-dominant pole. Now this amplifier, differential amplifier, also have the so-called zero. So again, we are not going to derive it. So we just simply using analysis at 0, omega naught equals to 0. Okay? So if this is equals to 0, your I out, which is given by IM4 minus IM2, also equals to 0. So basically, this current and this current, they are equal. And then for IM4, you can derive it. It's basically assuming this guy is half ID, this guy is negative half ID. So this guy will create this current, which is GM half VID. You will amplify, multiply by this guy, the impedance, which is given by the resistance 1 over GM 3 parallel with parallel with 1 over SCX. Is that right? This is 1 over GM3 resistor. This is correct. 1 over CX. Okay? So therefore, the total impedance is given by this guy over here. And then after you find the voltage at this point, you are going to have the current source generated simply multiplied by GM4. And your M2 is very straightforward. It's basically the minus VID over 2, okay, multiplied by GM2. And the two current has to be equal. So you equate them, equals to 0. And after some manipulation, if GM1 equals to GM2, GM3 equals to GM4, after some derivation, you end up omega Z1 equals to 2 GM3 over CX. So this is a simple way without actually go through the whole transfer function derivation and then look at the numerator equation. What is the 0? So this is a simple way to derive 0 by simply assume when output equals to 0, what is the corresponding frequency, so on and so forth. Okay, open loop versus feedback. One thing I want to mention is like, a lot of time people think, I design op-amp, I always need compensation. Is that true? If I design op-amp, I always need compensation. Compensation topic we'll talk about next lecture. I just want to ask you this question. If we design op-amp, do we really have to consider stability? Yes or no? So if you start designing op-amp, right thing, the first thing that you do is, I always, no matter what, have to make it stable. Is that true? How many say yes? I always to make it stable. How many say yes? Suddenly you guys chicken out. How many say no? You don't have to. How about the rest? It depends. You know me so well. It depends. Yes, it depends. Now, one common mistake students make is that they think design op-amp always need compensation, always need to consider stability. They forget open loop and feedback. If you are using the op-amp in the open loop manner, when do you use the op-amp as an open loop manner? Comparator? If you use op-amp as a comparator, do you care about compensation? You don't care. It's open loop. Do you care about stability? It's always stable, right? Because there is no feedback. So remember this, if it's open loop, this op-amp can be designed as this. You don't need compensation, you don't care about stability. It's always stable, but the bandwidth is limited. Okay, the bandwidth is limited. You have very high gain, but right away the bandwidth is dropped right away. Okay, the gain can be very, very high. Now, a lot of time we don't use op-amp in this way. Of course, comparator is one very extreme example. A lot of time we use op-amp in the feedback manner, like this. This is the op-amp function. We use some feedback factor F, feed it back, and then to create a closed loop function. Okay, so suppose this is the op-amp function, which has a dominant pole. And then after feedback, you are getting this guy, and then with a wider bandwidth. So effectively, what do we do? If the original op-amp have this kind of thing, after feedback, we are basically making it wider bandwidth, but the gain drop. So it's actually a trade-off between gain and bandwidth. We are using the very high gain of the op-amp, trade it off, make it lower gain but wider bandwidth. Okay? But to do that, you need to make sure the op-amp is stable. And you need to make sure compensate the op-amp such that the phase margin is sufficient. We will talk about that in the upcoming lecture. Okay? So when you do the feedback, a very important parameter is called loop gain. Loop gain. Okay? So you can see that. Why do we call it loop gain? You go through the loop. You have A multiplied by F, that becomes your loop gain. Okay, we call this guy loop gain. Now, in terms of frequency response, so this red color one is the original open loop of the op-amp. Okay, before feedback. Before feedback. Now, if you are doing the feedback now, due to the feedback, you are obtaining a new transfer function which have a lower gain. The gain drop by this loop gain factor, 1 plus A0 over F. So you are actually sacrificing this black region over here. In return, what do you gain? You gain wider bandwidth. If you stick with the original open loop, you get the bandwidth, the circuit is only good up to omega P1. But now, if you sacrifice this gray region or black region, you are able to extend the bandwidth by 1 plus A0 F. Okay, you extend the bandwidth wider. Now, some of you probably say, why? Why do I want to do that? I don't need feedback. I can still use this guy all the way. But amplifier design, you don't design in this manner because your gain change. Over this frequency, your gain change. At this, you have high gain. At this, the gain keep decreasing. You never design amplifier in this manner. Okay? This is a very expensive mistake. One of my students designed the RF amplifier. It just showed me the result. It works. But when the chip coming back, it doesn't work. I didn't check too carefully. Eventually, when it doesn't work, I go and check. He designed the RF amplifier over here. So in the simulation, everything works fine. But let's say due to the process corner, your gain suddenly dropped very drastically. You get the point? So in RF amplifier, it doesn't mean that, oh, it doesn't matter. At this frequency, I already have gain. So although I know the 3 dB is here, I don't care. You don't work that way. If you want to have frequency up to here, you better make sure it's flat all the way up to here. Okay, otherwise the process corner will easily kill your amplifier. Depends on the technology. So for 0.13, I think we are paying 20 to 30K. But recently the 22 nanometer that we're tapping out, we are costing euro 60K. No, more. I think I can't remember, 9 millimeter square maybe. Not a lot, but it's quite costly. No, cannot. If you want the one wafer, usually it's $1 million. So all the tape out, we are chopping the wafer into multiple 9 millimeter square and share with other people. Okay. And where are we? Okay, the loop gain. So here you can actually take out this portion and replot it. And this is actually what we call the loop gain. The loop gain. Loop gain is very important when you try to analyze the phase margin and all these things. We will talk about that probably next lecture. Okay, so here you can see that by using the feedback, one very good thing is you no longer rely on A naught. The final gain rely on the factor, feedback factor F. So if you go through this analysis, you see that somehow if A naught is so big, you cancel away A naught. Eventually the gain is only depend on the feedback factor. So in this example, it only depend on the register ratio. Register ratio. Why not depending on A naught is good? Because we make the mod RM, can you guarantee what kind of gain you are getting? You cannot. Because due to the process fluctuation, from chip to chip, the gain could be different, right? And even from batch to batch, the gain can also be different. So the gain fluctuates a lot. And let's say you don't like this vendor, you want to switch to the other vendor. This vendor have the RM that have a gain of 100. Switch to the other vendor could have a gain of 200. But using this feedback, do you care? You don't care. Because it doesn't matter whether it's 100 or 200. Eventually your gain only depends on register. That is the beauty of feedback. Okay, so here are some of the benefit of feedback. Okay, with open loop, very little voltage range, you are going to saturate the output voltage to either positive or negative 3 volt. But using the closed loop, you are able to widen the range, input range, okay, and make it more linear. Make it more linear as well. So open loop gain is high, but subjected to a lot of variation, which means sometimes you can get this, sometimes you can get even steeper, sometimes you can get gradual. There is no guarantee what you are getting. But once you design with the feedback, this slope is fixed, 10, always like that. Very stable. Feedback desensitize this variation, so I already mentioned. A naught can vary, but with the feedback, you remove the A naught factor, so you only depend on the R. And especially you only depend on the R ratio, actually R also doesn't matter. Okay? So for RF, usually it's open loop gain. We are dealing with very small voltage. The gain also not very high, but we are dealing with gigahertz range. The problem with feedback is like, you need to trade off very GBW, very wide, right? But you only use 1/10 of it. So if you design on M, that is 1 gigahertz. You only use 100 megahertz. So it's actually quite expensive. You try to use the feedback. You need to trade off the GBW with the actual frequency. So it's always lower than GBW. So in open loop, you don't have this one. In open loop, if you are able to make the parasitic small, you are able to make the GM larger, you can get whatever the bandwidth you want. That is the beauty. So IF, the amplitude is slightly larger, but the gain is still kind of limited. The bandwidth we are talking about, lower, but it's still quite high, 100 megahertz. And then for the baseband, we are talking even larger voltage, larger gain, but the frequency drop. Okay, so usually baseband, we can use feedback. Okay, IF, RF, due to the high bandwidth, wide bandwidth, usually we try to use open loop. So here is the derivation showing you how to desensitize the gain. So this is the closed loop gain. So if you are designing the amplifier using the open loop, this is the original gain. So you try to define delta A naught over, delta A naught over delta A naught. So that is basically just 1, right? Delta A naught over delta A naught, that is basically 1. Very sensitive. But here, if you try to design delta G over delta A naught, you are going to end up having this guy. So you can see that you actually divide the gain by this factor over here. So sort of desensitize the effect due to the N0. Root locus, another 2 slides, we are done. Now here we look at the pole. Actually looking at the pole, why we want to look at the transfer function and look at what is the pole? Because looking at the pole, you can sort of predict the behavior. For example, for RC or RL circuit, the pole is always real. It's always real. It falls under the negative real axis. And for this kind of thing, you know, you don't expect oscillation. You don't expect oscillation. There is no oscillation when the pole is like this. Now, if you have RLC circuit, that is where you start to have resonance. And that is when the pole happens here. This is when you cannot factorize the pole into a nice real component. You are going to have imaginary pole. So if you are going to have imaginary pole j omega, so you are going to end up having, so usually it means s squared, you cannot decompose it, it means you have s squared plus bs plus c, something like that. But you cannot factorize it further. If you factorize it further, you are going to get s plus a plus minus dj, plus dj or s plus a minus dj. So you are going to have complex pole. So if you have complex pole, it looks something like this. This kind of behavior, you look this kind of thing. So you have the oscillation frequency, but it will die down. The reason it die down is because you have a negative real part. Negative real part will give you minus sigma over here. So this minus sigma will have this exponential decaying behavior. Now, if you have pole located at exactly the j omega axis, you have oscillator. Okay, that one only have LC, so you have oscillator. So knowing where is the pole location actually allow you to predict the behavior of your system. Okay, so let's say this is the original S transfer function without feedback. If you introduce feedback, you are going to end up having a new transfer function. Okay, you introduce the feedback factor, so eventually you get something like this. You can rearrange this one and you end up having something like this. And you see that this is what we call the loop gain. Okay, the loop gain. And how the loop gain change actually affect the final system behavior. You can see that now this is your pole. Your original open loop pole is PS. But now this is your closed loop pole, which is PS plus A0F, or simply put PS plus T0. So it depends on what is your T0. Your pole will change. Because now you have to refactorize the polynomial. This is your new polynomial, P prime S equals to this guy. And it's a function of T0. So how is this pole changes? So here, not changes. Let's see. So let's say you have a one-pole system starting with omega P1. Now if you introduce the feedback, you are going to widen the dominant pole by a factor, 1 plus T0, the loop gain factor. And this basically just means that the pole is moving further away from the j omega axis. Okay? And it is always stable. So for this kind of feedback, you don't worry. So if you only have one pole system, you feedback with a linear factor. This system after feedback is always stable. It will not make the system unstable. Now, if you have a two-pole system, okay, originally it could be located at these 2 points, the two poles, separable. So if you don't introduce any feedback, you have T0 equal to 0. Now if you start introduce the feedback, T0 that is bigger than 1, or bigger than 0, you start to see these two poles merge. They are moving closer to each other, eventually they meet at this point. And it doesn't stop there. If you keep increasing the loop gain, you start to see the pole go into the imaginary side. Okay? That is where you start to have stability issue. Now, ideally, with two pole, after feedback, no matter what, you will still get two pole. And with two pole, if you think carefully, you always have phase margin bigger than 0. We will talk about phase margin later, but basically it means for two pole system, ideally it should also be stable. Okay? Ideally it should always be stable, because no matter what, even I move the pole higher and higher, I always fall under the left half plane. Am I right? If I fall under the left half plane, even I see oscillation, eventually it will die down. So no matter what, even two pole system with feedback, it should always be stable. But unfortunately, in real system, although you have two pole, you always have parasitic. This parasitic will add additional pole. So eventually you will see that although it might move like this way, but due to the additional pole, you will start to move closer and closer and eventually go into the right half plane. And once the pole go into the right half plane, unstable. Okay? Now, for three-pole system, it's only conditionally stable. So three-pole system originally, let's say this is the pole, when the feedback loop gain is actually 0. So now if you start increasing the loop gain T0, you will see this behavior. The non-dominant pole, omega P3, the one further away, will move even further away, go to infinity. Okay? Now, the one that is closer to the J omega axis will start to behave like the two-pole system. They are moving closer and closer to each other and eventually merge at this point. Once they merge, they don't go vertically. In fact, they go diagonally. Okay? So unlike this guy, they go vertically, they actually go diagonally in this manner. So eventually, if it go beyond to the right half plane, you have right half plane pole, the system will be unstable. Okay? So this just gives you a conceptual thing. How does the loop gain affect the overall closed loop system? If your original system is one pole or two pole, it doesn't matter what loop gain what feedback you get, it's always stable. But once you have three-pole system, depending on the amount of feedback, you could render an unstable system. So, okay, better than what I expect. I thought I'm going to last all the way to 9:30. Let's see. We can have the last one, then we can go. Do you need to scan the picture again? All done? Done? Okay. This one should be straightforward, right? I think you did listen to the lecture. You replied quite fast. Done? All done? Okay, let's move on. Good. So some of you didn't listen to the lecture. Okay, only reduced by 5 times. That is not true. Okay. A bit struggling, this question. All done? 20, 22. All done? Why this number keep fluctuating? Some of you are not making out your mind. Okay, you have to make up your mind. Ah, really? That is the case. Okay, let's look at that. Now, the first one you didn't choose, very good, because there is no such thing called right half plane pole. So if you pick this one, what can I say? I need to kick you out of my module. So right half plane pole never exists. Shouldn't choose it. Now, right half plane 0. At the right half plane, the 0 introduced negative 90 degree, not positive 90 degree. And left half plane 0 introduced positive 90 degree, not negative 90 degree. So the two are opposite. So the only correct one is the left half plane pole. Okay? Pay attention. Okay, I think that's it. So I'll see you next week, next Monday. So just a reminder, the next Monday, hand-in homework 2, project will be postponed to 18 April. Okay, 18 April.